Every time you scroll, stream, or click, you're tapping into a system that needs an astonishing amount of water. We think of the internet as intangible, an invisible cloud, but the physical infrastructure keeping it alive is surprisingly profoundly thirsty. How much are we talking about? A single large data center, the kind that powers your favorite apps and services, can consume millions of liters of water daily. That's enough to fill an Olympic swimming pool every few days. This massive hidden consumption begs a fundamental question. Why do these silent, humming buildings need so much liquid? The core reason is heat. Every scroll, every click, every piece of data processed generates it. Think of the microprocessors inside servers. Tiny, incredibly powerful brains performing trillions of calculations per second. This immense electrical activity, flowing through intricate circuits, converts energy into a colossal amount of thermal energy. Collectively, racks of servers can generate enough heat to turn a small room into an oven in minutes. Think of the microprocessors inside servers. Tiny, incredibly powerful brains performing trillions of calculations per second. This immense electrical activity, flowing through intricate circuits, converts energy into a colossal amount of thermal energy. Collectively, racks of servers can generate enough heat to turn a small room into an oven in minutes. So why can't we just use giant air conditioners? We can, to an extent, but air is not an efficient medium for heat transfer, especially at this industrial scale. The air inside a data center can reach over 40 degrees Celsius if left unchecked. Air conditioning systems for such heat loads are themselves incredibly energy-intensive and often struggle to cope with the sheer density of heat produced. To truly dissipate this heat effectively and economically, engineers turn to water. The most common and effective method is evaporative cooling, often called swamp cooling. It leverages a fundamental principle of physics. When water changes from a liquid to a gas, it absorbs a tremendous amount of energy, heat, from its surroundings. It's the same physics that cools your body when sweat evaporates from your skin. In data centers, hot air from the servers is routed over large cooling towers, where it comes into contact with recirculating water. The water absorbs the heat, a small portion evaporates and escapes as water vapor, carrying that energy away. The remaining cooler water is then sent back to continue absorbing more heat. In data centers, hot air from the servers is routed over large cooling towers, where it comes into contact with recirculating water. The water absorbs the heat, a small portion evaporates and escapes as water vapor, carrying that energy away. The remaining cooler water is then sent back to continue absorbing more heat. This process is remarkably efficient at removing heat, but it comes at a significant cost. That evaporated water is gone. This lost water needs constant replenishment. A single large data center can consume between 1 and 5 million gallons of water daily. That's often comparable to the daily water usage of a town with tens of thousands of residents. And it's not just any water. While some facilities can use recycled or non-potable water, many still draw from local municipal supplies, putting pressure on already strained water resources, especially in drought-prone regions. The hidden thirst of the internet isn't just about water consumption. It's also about the energy needed to pump, treat, and transport all that water. Are there other ways to cool these digital behemoths? Engineers are experimenting with innovative solutions like liquid immersion cooling, where servers are submerged in special non-conductive fluids, or advanced airside economization, which uses outside air directly when temperatures allow. These methods can dramatically reduce water use, but they come with their own complexities and aren't yet universally adopted. For now, the internet's reliance on water remains a critical challenge, so the next time you marvel at the seamless flow of information, remember the invisible, tangible infrastructure beneath it. Our increasingly digital world has a very real physical footprint, driven by the fundamental laws of thermodynamics and a surprising demand for one of Earth's most vital resources. How will we balance our increasing digital needs with the finite resources of our planet?